Lesson 25 is solving radical equations. So in 25.1, we're going to introduce solving them, and then 25.2 is talking about extraneous solutions. So 25.1, a radical equation is an equation that contains a variable inside the radical symbol. So you can see in all of our problems, they all have, in this case, like an x inside the radical, and that makes them radical equations. If you have an equation that has a radical, but like the variable is not in it, it would not really be classified as that. So for example, like x equals the square root of 4, that would be like a counterexample because it doesn't have the variable inside the radical. So for example, 1 through 4, we're going to solve and then check to see that the solutions are valid. So you check that by kind of checking any like algebraic answer, I guess, where you plug it back into the original equation and see if it makes both sides equal. We'll probably check the first couple, but then just for time's sake, we may not check all 4. It's really important in general to check all these solutions though, because with radical equations, you can get extraneous solutions, which mean equations or solutions that are not valid for that equation. Okay, so example 1, the cubed root of x squared equals 2. So the workbooks solve these equations using a little bit different strategy. It's totally up to you what you use. If you are interested in the other strategy, you can kind of read through it in the workbook. It has all the worked out problems, but just I tend to like prefer a different approach. Okay, so we have cubed root of x squared equals 2. When we're solving equations, like we usually use inverse operations, and it's no different here. It's just usually like the operations we see when we're solving simpler equations are like addition and subtraction or multiplication and division. Here we have like roots as well as exponents. So if I have the cubed root and I want to cancel it out, I have to use the inverse operation of a cubed root, which would be a third power. Like third root and third power, those cancel each other out. So in order to get rid of that radical, and remember when we're solving our goal is to just get x like completely by itself. So I have to undo the things that are being done to x. So if I want to cancel out a third root, I would raise both sides to the third power. And then the third power and the third root, those undo each other. So I would just be left with x squared. And then that equals 2 to the third power, which means 2 times 2 times 2, so that's 8. And then now my goal is to still just get x completely by itself, so now I have to cancel out that exponent. So the inverse of a squared exponent is a square root. And then the square root cancels out that power, and it leaves me with just x. And then remember, when we're solving for x and we take the square root of it, we have to include the positive and negative version. So it would be plus or minus the square root of 8. And then we just want to see if we can simplify that. So what I mean by that is like, does 8 have any perfect square factors? It does, because 8 is 4 times 2. So to simplify, we can just take the square root of the 4 and then leave the leftover 2 inside the radical. So it'd be x equals positive or negative. The square root of 4 is 2, and then the square root of 2 can't be simplified, so that part stays inside. So it's x equals positive or negative 2 root 2. And then if we want to check that, we need to take that solution and put it back in the equation where x is. We do typically want to check both the positive and the negative answers just to be safe. So for our check, it would be the cubed root of x. So I'll make the first one to the positive 2 root 2. Raise the third power, no, raise the second power, sorry. So this one in for x, and then that's equal to 2 on the other side, was the original problem. And then if we take like 2 root 2 and square that, we got 2 root 2 from like simplifying the square root of 8. So this is basically the square root of 8 just like having been simplified. So if I take the square root of 8 and I square it, it just cancels out the radical. So that would leave me with the cubed root of just a regular 8. So one more time, like if I were to take the square root of 8 and I were to square it, it just leaves me with an 8 inside the radical. Another way of thinking of it is like this power cancels out this radical. So it just puts the 8 in the overall like cubed root radical. And then that's equal to 2, and then the cubed root of 8 is 2. Like, that's true. So we end up with 2 equals 2, so that check worked. And then the other one, we just want to kind of repeat the same process, but with a negative x value. So the second check is the cubed root of, in this case, negative 2 root 2 squared, and then that's equal to 2. So when I square something, it always ends up being positive no matter what. So if I raise negative 2 root 2 to the second power, it's going to end up being the same thing as if I did positive 2 root 2, because squaring a number always turns it positive. Like negative 4 squared would be negative 4 times negative 4, which is a positive 16. So this simplifies the same way. So it would become just the cubed root of 8, and then that's equal to 2. And then the cubed root of 8 is 2 because it's 2 times 2 times 2 is 8. So our check worked there as well. So both of these solutions are valid. These, like this entire section, 25.1, all of the solutions will be valid. So that's the last check I'm going to do for this section. But just know if it's a problem where, you know, it's not separated out by like regular solutions and extraneous solutions like in 25.2, it's best practice to always check your solutions. Okay, so example 2, the square root of 9x minus 20 is equal to x. So I want to get rid of that radical. It's kind of messing up my like x, or it's trapping it in there, at least one of them. So in order to cancel out a square root, I have to use a squared exponent. So I'm going to go ahead and square both sides right away. That power cancels out the radical. Those are inverses, and I'm left with just what was inside of the radical. So I'm left with 9x minus 20 equals x squared. And then now that I've like squared both sides and I have an x squared term, I have a quadratic. So if I have a quadratic, I need to solve it by putting it in standard form first. So that means that everything is on one side of the equal sign. You can subtract the x squared over. I like to keep that term positive. So if you subtracted it over, you would need to divide the equation by 1. Instead of that, I'm just going to go ahead and subtract the 9x over after the x squared, and then add the 20 over after the 9x. So these will cancel, and then I'll be left with 0 is equal to x squared minus 9x plus 20. And then now I have a quadratic in standard form. A is 1, so I just need numbers that multiply to C, which is 20, and then add up to B, which is negative 9. Those two numbers are negative 4 and negative 5, so that's how I'm going to factor it. So it'll be 0 is equal to, that x squared term breaks down into x, and then those numbers that we found that multiplied to 20 and added up to negative 9, those fill in the rest. So negative 4, negative 5, and then the order here does not matter. You can put the negative 5 first if you want. And then the final step for solving is to just go ahead and get all the way down to like x equals. So I'm going to bump this up just because I ran out of space a little bit. But now my equation is factored completely, so I just need to set each factor equal to 0. So I'll do x minus 4 equals 0, x minus 5 equals 0, and then I'll solve each equation separately. So for x minus 4, I have to get the x by itself, so I need to add 4 over, get x equals positive 4, and then for the x minus 5, I got to undo that minus 5, so I'm going to add 5 to both sides, and get x equals positive 5. So x equals 4 and x equals 5, and again, like, best practice to take both of these and put them back into the equation. But for the video's sake, I'm going to kind of skip that step. So example 3, 5 times the square root of 2x minus 3 plus 2 is equal to 27. So we have another radical. We're eventually going to want to cancel it out. But before we can cancel out the radical, we want to try to make sure it's as isolated as possible. So right here, the radical is the square root of 2x minus 3 but I have a 5 that's in front of it. It's being multiplied by the radical. And then I have a 2 that's being added outside of the radical. Anything that's outside of the radical, we can cancel out. Anything that's inside, we have to wait until we can get rid of the radical itself. So it's really important to, if at all possible, cancel out the things that are outside of the radical, because if, like, we tried to cancel it out, like square both sides from the first step, it'd be pretty hard because we'd have to like FOIL with the radical. It'd be, I don't recommend it. Okay, but we can definitely go ahead and cancel out this 2 that's being added. So like the opposite of adding 2 is subtracting 2, so I could subtract 2 from both sides. And then I bring down this whole thing, so 5 times the square root of 2x minus 3. The 2 minus 2, that cancels out. And then I have 27 minus 2, which is 25. And then I still have that 5 that's being multiplied by the radical, so I can undo multiplication with division. So divide both sides by 5. 5 divided by 5, that'll cancel out, and then it'll leave me with just the radical. So 2x minus 3. And then 25 divided by 5 is 5. So now the radical is isolated. We can't, unfortunately, not really unfortunately, it doesn't make a huge difference. We can't get rid of anything inside the radical. Think of it as like kind of like a jail cell, like nothing comes out of it. But now that the radical is isolated, it's relatively quick to cancel it out. So the opposite of a radical, like a square root, is squaring something. So in order to get rid of that radical, I have to square both sides. So squaring the radical just cancels it out, and it leaves me with what was originally inside. So 2x minus 3, and then is equal to 5 squared, which is 25. And then now I have a linear equation where I'm just trying to get x by itself. So to undo that 3 that's being subtracted, I will add 3. So then I have 2x. Negative 3 plus 3 cancels out. 25 plus 3 is 28. And then from there, I have a 2 that's being multiplied by the x, so I'm going to divide both sides by 2. So I end up with x equals 28 divided by 2, so 14. So x equals 14. Same thing as before, like it's always a good idea to check. I know, like, we know that this whole section, the solutions will be valid because the next section is when we're going to get to extraneous though. So I'm going to skip it for this section and we'll do it in 25.2. Okay, so example 4, this is a really good point to where, like, if you're comfortable, pause the video, test it on your own, see if we get to the same answer at the end. If not, just kind of watch it as another regular example. So the cubed root of x squared plus 6x equals negative 2. So this time I have a radical that's isolated, but it's a cubed root. So if I want to cancel out the cubed root, I have to cube both sides. So the exponent and the type of root, those need to match. And then just as like a general reminder, if you don't see like the type of root, it's always a square root. You would just never write the 2 in front. You would just only see other numbers. Okay, so I'll raise the left side to the third power and the right side. So especially because this is a cubed root, well, I don't even want to say that. It's important, or not cubed root, but cubed power. I don't even want to say like especially because of that, because it's always important. You have to recognize that we're raising this entire thing to the third power. So I have to do like negative 2 times negative 2 times negative 2. The negative has to be involved every single time. So the cubed root and the cubed power cancel each other out, so I'm left with just what was inside. So x squared plus 6x. And then negative 2 to the third power is negative 2 times negative 2, which is a positive 4. Times another negative 2 would be a negative 8. And then now I have an x squared, so I have a quadratic. I want to try to get it in standard form. So I have to get everything on one side equal to 0. So I'm going to add 8 to get a 0 on the right side of the equal sign. And then I'll add it after the 6x. So x squared plus 6x plus 8 is equal to 0. So quadratic in standard form. A is 1 again. So I just need numbers that multiply to c, which is 8, and add up to b, which is 6. So multiplies to 8, adds up to 6. That'd be 2 times 4. So the x squared breaks down into x and x, and then the 2 and the 4 fill in the rest. So since they're both positive, it'll be plus 2 and plus 4 is equal to 0. And then now it is factored completely, so I'm ready to go ahead and just set my factors equal to 0. So one factor is x plus 2. Set that equal to 0. The other factor, x plus 4. Set that equal to 0. And then for x plus 2, we have to cancel out the 2 that's being added, so we'll subtract 2 from both sides, get x equals -2. For x plus 4, we have to undo the 4 that's being added, so we'll subtract 4 from both sides, get x equals -4. So x equals -2 and x equals -4 are our solutions. So 25.2 is still solving, it's just we end up with equations that have extraneous solutions. So extraneous solutions are solutions that make the equation not valid, meaning that when you check them, the check just doesn't work. So example 1 and 2, we will solve both and then check both answers. So for example 1, the square root of 3x minus 2 plus 4 is equal to x. So always the objective should be to isolate the radical. There are certain cases where it's more difficult. They don't pop up in the workbooks of the checkpoint, but you could potentially see them in the future. But if at all possible, get the radical completely by itself. So as far as what's going on outside of the radical, but on its side of the equal sign, is just that plus 4. So if we want to undo that plus 4, we'll subtract it over. Bring down the radical. So 3x minus 2 is equal to 4 minus 4, that cancels, and then x minus 4. So the radicals by itself, I'm ready to go ahead and square both sides to get rid of that square root. So I'll square this side, and then on the right side, because it's two terms, x and then the -4, when we square it, we have to square the entire quantity, which means we're going to have to FOIL it. So on the left side, squaring it just cancels out the radical. So 3x minus 2 is left over, just what was inside the radical initially. And then on the right side of the equal sign, I'm going to expand this, so x minus 4 times x minus 4. And then we're going to end up with a quadratic once we multiply the x's together, so our goal should be just to work on getting it in standard form first. So I know that this part feels kind of like tedious. Well, why did I subtract over the 4 if I was just going to have to FOIL it? And if we didn't do that, like if we say just tried to square this whole thing initially, well, this is like one big term and this is another, so we'd have to FOIL that with the radical, which is less than ideal. It's kind of a pain in the butt. Okay, so I'm going to leave the 3x minus 2 alone for right now and then FOIL on the right side. So x times x is x squared, and then x times -4 is a -4x, and then -4 times x is a -4x as well, and then -4 times -4 would be a positive 16. And then we'll go ahead and combine like terms. So, the two -4x's, we can combine those. We already have them combined, but 3x minus 2 is equal to x squared. -4x minus 4x is -8x, and then bring down the plus 16. And then now we can get everything on one side of the equal sign. So to do that, I have to subtract over the 3x because it's positive 3x. I'm going to subtract it from the 8x because those are like terms. And then I can add over the 2 since a -2, and I'll add that under the 16 since those are like terms. So these will cancel out entirely. I'll be left with 0 is equal to x squared. -8x minus 3x is -11x. And then 16 plus 2 is 18. So we end up with, again, a quadratic standard form now. A is 1, so I need numbers that multiply to 18, add up to -11. So that combo would be -2 and -9. So 0 is equal to the x squared breaks down into x, and then the combo that we found fills in the rest, so -2, -9. And then we can set each factor equal to 0. So x minus 2 equals 0. X minus 9 equals 0. And then we can solve each separately. So if we add 2 to both sides, we end up with an x equals positive 2. Add 9 to both sides over here, end up with an x equals positive 9. So we have x equals 2 and then x equals 9. We are going to check both of these though and see if they both work or if one of them doesn't. See what happens. So to check, we need our original equation. So I'm just going to rewrite it up here and then I'll swap out my x's for like our actual solutions. So 3x minus 2 plus 4 is equal to x. That's my original. Just going to copy it really quick. And then for our check, it doesn't matter which one you check first. I will check the 2 first. So check the 2. I'm going to take out the x's. Take out the x's, replace those with 2's. And then can't forget the one on the other side as well. And then now just simplify. So inside the radical, work on simplifying that. Let's see, 3 times 2 is 6 minus 2 altogether, that's 4. Plus 4 is equal to 2. Sorry if that was a little bit quick. So 3 times 2 is 6, and then 6 minus 2 is 4. So that's why we ended up with a 4 inside the radical. And then I can take the square root of 4, which is 2, plus 4, and then bring down the equals 2, and then 2 plus 4 is 6, which is not 2. So that's an example of a solution that is extraneous. So we would just like cross it off on your work. You may be asked like specifically like what is the extraneous solution, and you would want to identify that 2 is an extraneous solution. It is possible on like rare cases that they both are extraneous, so you always want to check for both. So we'll check the second one. Just gonna copy this again. And then the second solution was 9. So I'll check 9 next. I'm going to take out the x's and replace them with 9's. And then simplify. So inside the radical, let's see, this is a 3 times 9, which is 27, and then 27 minus 2 is 25, so we have a 25 inside the radical, plus 4 is equal to 9. The square root of 25 is 5, plus 4 is equal to 9, and then 5 plus 4 is 9. So this one did work, so that one's good. Okay, so for this one, x equals 9 would be our valid solution, and then x equals 2 would be our extraneous solution. Okay, last problem, the square root of 13x minus 10 is equal to x plus 2. This time the radical is already isolated for us, so that's nice. Just get to square both sides right away. Same as the last problem where x is a term, 2 is another term, so I have to square them together and I'll have to like expand and FOIL. So squaring the radical just cancels it out. And then I have left what was inside, 13x minus 10. And then the x plus 2, I'm going to go ahead and just kind of expand it in the middle. So I could just save a little bit of writing or a little bit of room at least. So x plus 2 times x plus 2. And again, you have to FOIL or like expand like that anytime there's multiple terms inside the parentheses and like terms are separated by plus or minus. So x would be a term and 2 would be another term. Okay, and then if we FOIL it, x times x, that's x squared. And then x times 2 is plus 2x. The middle 2 times x is another plus 2x. Feel free to just combine those two x's right away. And then the last would be 2 times 2, so plus 4. And then check for like terms. I have a 2x and a 2x that I can combine. So 13x minus 10 is equal to x squared. 2x plus 2x is 4x, and then bring down the plus 4. And then now I can get everything on one side. Since I have a quadratic, I'm most likely going to have to factor it or use another method for solving it. So first step is just getting everything on one side of the equal sign. So I'll subtract over the 13x. I'm going to line it up under the 4x. I will add over the 10, line it up under the 4, so that it's all lined up with their like terms. These both cancel out to 0, so this is going to be a 0 right here. And then x squared. 4x minus 13x is 9x, and then 4 plus 10 is 14. And then now, same situation, I have a quadratic where a is 1. So if I want to try to factor it, I'm looking for numbers that multiply to c, which is 14, and add up to b, which is -9. And all of these problems, like, if you weren't super comfortable with factoring, like, you could have used the quadratic formula or completing the square. It's just, they were factorable, so usually if things are factorable, that's the method that we try to go with, because it's usually the fastest. Okay, so for multiplies to 14 and adds up to -9, that combo is -2 and -7. So then that means that the x squared breaks down into x and x again. That's always the case when it's a 1x squared. That's why we're able to factor it a little bit quicker this way. And then the combo fills in the rest. So -2, -7. And then now we can set each factor equal to 0. So x minus 2 equals 0, x minus 7 equals 0, and then use inverse operations to solve both. So x minus 2, I'm going to add 2 to both sides, get x equals 2. X minus 7, I'm going to add 7 to both sides, so I end up with x equals +7. So x equals 2 and x equals 7, and then we will check both. So I'm going to rewrite the original equation up here, so 13 x minus 10 is equal to x plus 2. So for the first check, I'm going to check the x equals 2. So I'll take out my x's and go ahead and put 2's there, since we're checking x equals 2. And then if I simplify inside the radical, 13 times 2 is 26, and then minus 10 would be 16. And then is equal to 2 plus 2, so that's 4. The square root of 16 is 4, so we end up with 4 equals 4. So that checked work. So definitely x equals 2 is good. And then we'll check x equals 7 next. So I'm going to go ahead and just recopy this down for the second check. So I have to take out, if I'm checking x equals 7, I'll take out my x's and replace them with 7's. And then 13 times 7, I don't know exactly what that is. Let me grab a calculator. 13 times 7, 91. I don't think I would have guessed that. Okay, so 13 times 7 is 91, and then 91 minus 10 is 81. And then that's equal to 7 plus 2, which is 9. Square root of 81 is 9, so we end up with 9 equals 9. So both of these worked. So in this case, like, both answers are perfectly valid. They're perfectly fine. There's no extraneous solutions here. And that just sometimes happens. So sometimes there can be no extraneous solutions. Sometimes there's one. Sometimes there's two.